Here is a situation that has frustrated engineers on every platform, at every scale, since auto-scaling was first introduced. You have configured your infrastructure carefully. Your scaling policies are in place. Your thresholds are sensible. You have tested it. Everything looks right. Then a traffic spike arrives. A product launch, a news mention, a flash sale. And for the first 2 minutes, your application slows to a crawl. Requests pile up. Response times stretch. Some users hit errors. Then the new servers come online, the load distributes, and performance recovers. The auto-scaling worked. It added the capacity you needed. It just didn't do it fast enough to prevent the pain. This is not a bug. It is not a misconfiguration. It is the consequence of something that nobody tells you when they explain auto-scaling. Scaling takes time, not because cloud providers are slow, and not because anything went wrong, because bringing new capacity online is a process, and every process has a duration. Think about a restaurant on a Saturday night that gets unexpectedly slammed. Tables fill faster than expected. The kitchen is falling behind, and the manager decides to call in 2 extra staff members who are off that evening. The call goes out. The staff agree to come in, but they are not already standing in the kitchen. They have to get ready at home, travel across the city, arrive at the restaurant, be briefed on tonight's menu and specials, clock in, and find their footing before they are actually capable of serving a single table. From the moment the manager recognized the problem to the moment the extra staff are genuinely contributing, 45 minutes might have passed. The dining room was suffering for the entire duration. Not because the manager made the wrong call, calling them in was exactly right, but because there is an irreducible minimum amount of time between deciding you need more capacity and that capacity being real, present, and working. Auto-scaling has the same structure. The gap between a traffic spike arriving and new servers genuinely handling requests is not a single delay. It is a pipeline of delays, each one necessary, each one adding to the total. Understanding the pipeline is what separates engineers who are surprised by scaling lag from engineers who have priced it into their expectations and designed around it. The pipeline has 4 phases. The first is detection. Your auto-scaling policy is watching a metric, CPU utilization, request queue depth, response latency, whichever signal you configured, but it is not watching that metric in real time at the granularity of individual seconds. It is sampling it on an interval, typically every 60 seconds for many cloud platforms, sometimes every 30. That means a spike that begins at 14 hours, 0 minutes, and 0 seconds might not be visible to the scaling policy until 14 hours, 1 minute, and 0 seconds at the earliest. The world changed a full minute before the system that responds to the world knew about it. The second phase is decision. Most scaling policies require a metric to sustain a threshold for a period of time before acting. The cooldown period covered in this series' previous video. This is deliberate. A CPU spike that lasts 20 seconds is noise. One that holds for 5 minutes is a pattern worth responding to. That evaluation period adds more time. By the time the policy has confirmed that the condition is real and persistent, several minutes may have elapsed since the spike began. The third phase is provisioning. Once the decision is made, the cloud infrastructure must allocate new compute instances, boot an operating system, attach storage, configure networking, and register the new servers with the load balancer so that traffic can begin flowing to them. On a well-provisioned platform, this takes between 1 and 3 minutes for standard virtual machines. Container-based workloads can do it faster, sometimes in seconds, but it is never instant. Physical resources have to be allocated, operating environments have to be initialized, network routing has to be updated. This phase has a flaw that no amount of configuration reduces to 0. The fourth phase is warm-up. This is the one that surprises people most, and it is worth spending time on. A new server that has finished provisioning is not the same thing as a new server that is ready to handle your application's traffic at full speed. Modern applications are not static. They have startup sequences. A web server initializes its thread pool. A database connection pool opens and authenticates its connections. A caching layer starts empty and has to populate itself through actual requests before it stops going to the underlying database for every single query. In languages that use just-in-time compilation, Java and the JVM being the most common example, the first few hundred requests through a new instance are slower than the steady state, because the runtime is still compiling the most frequently executed code paths into optimized machine code. The instance is alive, it is in rotation, and it is slower than it will be in 10 minutes. This is what engineers mean when they talk about cold starts. An instance that has never served traffic is cold. All of its internal state is empty. All of its optimization is unintelligized. All of its cached data is missing. A cold instance handling real requests under load produces response times that can be 2 or 3 times slower than a warm instance doing the same work. Add 10 cold instances during a spike, and you have added capacity that is technically present but practically degraded, exactly at the moment when you needed that capacity most. None of this is a flaw in the design. It reflects a real constraint. Bringing a new server online takes time, and making it operate at full efficiency takes more time still. The question is not how to eliminate this latency. It cannot be eliminated, but how to shrink it. Several approaches exist and are genuinely effective. Scheduled scaling, introduced in the context of auto-scaling policies, is one of the most powerful. If you know a spike is coming, a scheduled product launch, a daily traffic peak that arrives every morning at the same time, you can instruct the system to add capacity before the demand arrives. The instances provision and warm up during the quiet period that precedes the spike, so that by the time traffic rises, the servers are already warm and ready. Pre-warming eliminates the lag entirely for predictable events, at the cost of running slightly more infrastructure than you currently need. A second approach is maintaining a minimum number of warm instances at all times, even during low traffic periods. Rather than scaling down to the absolute minimum during quiet hours, you keep a small standing pool of warm servers in rotation. When a spike arrives, these instances absorb the initial surge, while new capacity provisions. The first 2 minutes of a spike hit warm servers rather than cold ones. The degradation window shrinks, sometimes to nothing. A third approach, more architectural than operational, is reducing warm-up time at the application level. Faster startup sequences, smaller caches that fill quickly, connection pooling strategies that front-load initializations. These do not eliminate cold starts, but they reduce the duration of the cold period so that new instances reach full efficiency sooner. What you understand now is that scaling lag is not a symptom of misconfigured infrastructure. It is the sum of 4 real, distinct, unavoidable phases: the time to detect a change, the time to confirm it is real, the time to provision new capacity, and the time for that capacity to reach full operating efficiency. Each phase has a flaw. The total has a flaw. The goal is to push that flaw down as far as possible through a combination of predictive scaling, warm instance pools, and faster application initialization, and then to design your system with the honest awareness that some gap will always remain. Infrastructure that accounts for the gap handles spikes more gracefully than infrastructure that assumes scaling is instantaneous. The spike arrives either way. What differs is whether the first 2 minutes are a surprise or a known quantity you have already prepared for.